Alright, so let's look at the second question. So we want to design an analog Butterworth filter, and to do that we need to figure out the order of the Butterworth filter first. Okay, here is a diagram from Wikipedia. So you can see for the low pass filter, when frequency is low, we pass it. When the frequency is higher than the cutoff frequency, we can attenuate it. Okay, so when the order is low, the slope is not steep, and when you increase the order, the transition from pass band to stop band gonna be very narrow. So we want to change it very fast. The cost is you have a more components, so higher orders. All right, so we need to know at least 2 points to find the slope. Okay, so if you read this one, we will see first we know the cutoff frequency at omega c. Okay, so we know the first frequency is 20 radians per second, and its corresponding attenuation is negative 3 dB. Okay, so we got this one first, and then we know at omega 2, which is a 40, okay, we got another attenuation rate, which is negative 10 dB. All right, so we know 1 point, we know another point, so we can plug in to this equation to find out the order. Okay, after that, we gonna choose one of this denominator as the template. Then we replace this to plug in omega s. Okay, let's do that. So plug in, so to find out n. Okay, n equals to log 10, and plug in this 10 to the order of negative 3 divided by 10. So there is already a negative, so k1 negative is positive, so we got a positive 0.3 and a minus 1 divided by 10, which is negative 10, and another negative, so makes it positive, so 1 minus 1, and that is the, put it into the log. Okay, and that's the numerator, and denominator is 2 log 10 omega 1 over omega 2, which is 20 over 40, and that's it. Okay, that's for the n. If you use your calculator, you will get, what I get here is log 10 inside of this part. I will change another color. This part becomes 1.995, so minus 1 becomes 0.5, so this is 10, right? So this whole thing becomes a 9. All right, so what I get here is 0.995 divided by 9, which is, inside this one I got 0.11. all right, and divided by 2 log 10, 0.5, so what I got on the top is negative 0.95, what I got bottom is negative 0.602, so in the end the n is 1.57. That's what I get. And you know the order, sorry, I still need this one, so the order of your equation need to be an integer, okay, need to be an integer, so we take 2. Okay, so 2 is enough, right? So it gave you the enough attenuation at certain band when is not satisfactory. So we're going to choose this one as the denominator. Okay, so you will have a prototype. It's look like this. So H analog S equals to 1 over S squared plus root 2S plus 1. So this is the template, normalized. That means the cutoff frequency for this one is 1. Okay, our cutoff frequency is not 1, and so we need to bring it into a new cutoff frequency. So we use the this one. Okay, low pass filter to low pass filter. You just put the new frequency in. Okay, this template can also be used to design a high pass filter or band pass filter. That S will equals to a different thing. So that S, you're going to replace S with S over 20. So the new one, H hat S, going to equals to S over 20 square plus root 2 S over 20 plus 1 and 1 over it. Okay, then we start to do the math. So 400 S squared plus root 2 S over 20 plus 1 over it. Sorry, this equal should be here. And then we want to put the 400 and go up. So we have this 400 at the top, S squared plus root 2, 20S plus 400. So everything multiplies 400. In the end, we got 400 divided by S squared plus 28.28 S plus 400. Okay, that's the result. So first you need to determine N, and then you want to customize the template using this one. So you bring in the cutoff frequency.